I remind you something, and let me just give a little bit more information about what we spoke about deleting weakly dominated strategies. So we proved that iterative deletion of weakly dominated strategies, when we look at domination in the mixed sense, introduces no new mixed Nash equilibria. Now, I remind you that being weakly dominated means that the strategy is there exists a strategy which weakly dominates that, and weakly dominated means that the strategy is always at least as good than the strategy it weakly dominates, and there is at least one setting of the other players when it's strictly better. Now, let me actually go to the definition. Maybe it will be simpler if we just look at the definition. Yes. So strategy SI is weakly dominated. Here it's in the passive version by P prime, by a mixed strategy, if SI always gives at most what P prime gives for any setting of the others, and there exists a setting of the other players, so a subprofile S prime minus I, where SI is yields us strictly less than P prime I gives. That means weakly dominated. Now, we can also talk about being always strictly less. So it can be either the same or sometimes strictly less. So we can also remove the requirement for being at least once strictly less, and that's what we call very weakly dominated. Let me, yeah. So what I want to say is that the proposition that iterative deletion of weakly dominated strategies in the mixed sense introduce no new mixed Nash equilibria also holds if we only require the domination be very weakly dominated. Intuitively, it also makes sense, and now let us formally say what it means. So first of all, given a game, strategy SI is very weakly dominated by the mixed strategy P prime I if the utility of SI is always at most what Pi prime I gives for any setting of the other players, and there is no requirement for the strict inequality to sometimes hold, so this can be exactly the same. And then, well, having defined what it means that SI is weakly dominated in the mixed sense by P prime, we say that strategy SI is weakly dominated, very weakly dominated in the mixed sense. And I remind you that you don't say it makes sense in general because we assume that unless we say otherwise. So SI is very weakly dominated if there exists some P prime I that such that SI is very weakly dominated by that P prime I. And of course, as we see that being weakly dominated introduces its very weakly dominated because implies it's very weakly dominated because being weakly has another requirement of sometimes having this strict inequality. And as I've mentioned, with pretty much the same, with the same analogous proof, we can also state that iterative deletion of very weakly dominated strategies in the mixed sense also not only uh, weakly but also very weakly dominated strategies introduce no new mixed Nash equilibria. Okay, so we already saw this example, and now let us give another important but not really something we are going to dwell on in this course much. The notion of a strict equilibria, and that's the following: that a profile is a strict Nash equilibrium if for any player and for any setting of the other players' strategies, the utility of that player in this profile is strictly better than the utility of that player for any possible deviation S prime I. So in the definition of a Nash equilibrium, we require that nobody can improve, but here we require that any unilateral deviation will strictly decrease the deviator's utility. Not only will it not improve, but it will strictly decrease. It's a requirement which is of course stronger than the requirement of a Nash equilibrium, and being a strict mixed Nash equilibrium analogously is defined as being a strict Nash equilibrium in the mixed extension. I remind you what the mixed extension is. When we look at all the possible probability distributions on the strategies and define the utility according to the expectation, using the assumption that we can have this utility which fulfills the conditions of von Neumann-Morgenstern theorem. So that's how we can define all this for the case of strict Nash equilibria. But as I said, that we are going to mostly deal with normal Nash equilibria in the context of non-cooperative games. So unless we explicitly say otherwise, we deal with non-strict Nash equilibria. And now let us talk about the deletion of weakly dominated strategies. So are they indeed indispensable? That's a very interesting question, because we prove that their deletion cannot add Nash equilibria. Now we know that there can be Nash equilibria containing weakly dominated strategies. So their deletion is not for nothing. It's not like deleting strictly dominated strategies. So on the first glance, or at least not on the first glance, to a certain extent, in a certain sense, weakly dominated strategies are indispensable. So let's look at some examples from this book by Osborne. By the way, don't confuse this, please. So there's a book by Osborne and Rubinstein, and there is a book by Osborne. So these are two different books. I think the one by Osborne and Rubinstein is more famous, but both books can be used. And the example I'm looking at is the following. So look at this two-player game. The row player has top and bottom, and the column player has left and right. Here, the top strategy weakly dominates bottom, right? Why? One is strictly larger than 0, and 0 is equal to 0. So there is a weak domination. And the left strategy weakly dominates right for the column player. So 1 is strictly larger than 0, but 0 is equal to, of course, to itself. Now the set of pure Nash equilibria here is top left and bottom right. So bottom right consists of two weakly dominant strategies. The top left consists of no weakly dominant strategies, but there is also an equilibrium which consists of two weakly dominant strategies. And another example is a similar, not a similar, but okay, it's another matrix. Here also top weakly dominates bottom, because 1 is strictly larger than 0 and 2 is equal to 2, and left weakly dominates right. 1 is strictly larger than 0 and 2 is equal to 2. And the same as before, the pure equilibria top left and bottom right. And bottom right, as we said, consists of two weakly dominated strategies, while top left contains no weakly dominated strategies. Now the interesting part is, let us look at the social welfare of this equilibrium. You can stop the video and think of that yourself. So first of all, what is social welfare? I remind you that's the sum of the utilities of the players. Now, the utilities of the players, they're written in the matrix. So, in the case of the first game, the sum of the utilities of the players in the first equilibrium is 1 plus 1 is 2, while in the equilibrium, which is made of only weakly dominated strategies, it's 0 plus 0. So it's a kind of intuitively, in a way, that the dominated strategies give something less than the non-dominated. Again, that's not exactly, and that's exactly the point. So in the second example, the social welfare, the total utility, in the equilibrium consisting of no dominated strategy, top left, the social welfare is 1 plus 1, it's 2. Now, if we look at the equilibrium consisting of the weakly dominated strategies, however, bottom right, then it's 2 plus 2, which is 4. So being weakly dominated does not prevent them from having a higher equilibrium value. Now, the counterintuitive flavor is very, I think it's prominent. That's a nice example. Now, why is that? Because the domination expresses itself outside of this square bottom right. So 1 is strictly equal than 0, but 0 is here. And this 1 is strictly equal than 0, which is here. And we are talking about that square when we look at the social welfare at the equilibrium, which consists of two weakly dominated strategies. So that's a nice example. By the way, those examples are also they are both symmetric, and they're going to talk about symmetric equilibria later. By the way, please notice that despite that they're symmetric, no, actually not despite. Here, of all the equilibrium are also on the diagonal, but that's not always the case. So we are going to talk about that later. That's not an example which relates to symmetry. That's so anyway. These examples show that weakly dominant strategies can be indispensable when analyzing equilibria. Simply, if we remove them, then we are left with only one square, and so we have lost one equilibrium. They are indispensable in that sense. Now, another important example is that not only can we have a Nash equilibrium, which contains only weakly dominated strategies, we can also have an Nash equilibrium which contains weakly dominant strategies and which is unique. So in this example, again from that book, the only pure equilibrium is bottom center. Now that equilibrium contains only weakly dominant strategies. Bottom is weakly dominated by top, 1, 0, 1, 1, and 1, 0 when I compare the values. And center is weakly dominated by, well, either left or right, by both. Like 0 is smaller than 1, and 0 is 0, 0, 0. Oh, here, 0, 0, 0 smaller than 1, 0, 0. So you can check that these two weakly dominant strategies indeed yield an equilibrium here. And that's also the important thing, is that that's the only one. However, if we look at the mixed extension, then there is a theorem which we do not prove, and that's that in a finite game, there exists a mixed extension, a mixed Nash equilibrium with no weakly dominant strategy in the support. So in the previous example, we can in particular infer from the theorem that there exists a mixed Nash equilibrium which is not pure, because the only pure equilibrium has only weakly dominated strategies in the support. Okay. So having dealt with that and said that, yeah, weakly dominated strategies are indispensable, only that in a finite game there exists a mixed Nash equilibrium with no of those in the support. It still can be that we lose some equilibria if we remove those, delete those strategies. Having dealt with that, let us look at the interplay between security, how secure you are at what you do, at what you get, and stability. So basically max min, what you can guarantee, that security, and the stability of the profile, the interaction, the stability of the interaction. So the idea of Nash equilibria is about stability. It's one of the possible definitions of stability, probably the most widely used one in the realm of non-cooperative games. And the max min, what the best you can do against the worst attitude of the other, is something which has the intuitive meaning of security. Now, in the case of constant sum games, we proved that the Nash equilibrium in a constant sum game, it's a typo, it's not is, it's in. Let me check. In a constant sum game, they're exactly the max min profile. So in the constant sum games, we have this identity between security and stability. Now, in general games, that's not always the case. So let us look at the example from Machler, Solon, and Zamir, where they show that the only Nash equilibrium here is bottom right. Pure, I'm talking about pure. Now, that's indeed stable by the definition of, in the sense of Nash equilibrium, but that unique Nash equilibrium, indeed unique, is dangerous. It's not safe because if player 2 chooses to go to use L instead of R, say by mistake or whatever reason, let's say that because the assumption of playing a Nash equilibrium is reasonable, but maybe it doesn't play according to that. So if you choose L, then player 1 would suffer. It would get minus 100 instead of 3. It would suffer a lot. So that actually motivates player 1 to say, okay, let me choose the safest option, which is something which, regardless what player 2 chooses, I don't get something really bad. So bottom gives the worst case can be 100 minus 100. Middle gives the row player the worst case 10 minus 10, and top gives the row player the worst case 2. So what if player 1 chooses the safest 2? Now if that's what she does, then 2 says okay, but player 2 says, the column player says, now if I keep playing R right, I will get not 3 as I hoped to, but minus 20. So I need also to think of what do I do to be safe. So playing L is safe because then the worst case is 0, unlike minus 20 if the column player plays R. So here player 2 is motivated to choose the safest option L. And now that going back exacerbates the fears of player one that, yeah, maybe I should, player one can think I should not play bottom because the second player can play L for whatever reason she may have. And then player one again is motivated to choose T, and then player two is motivated to choose L, and that's cyclic. So we have a reason, that's an example to give a reason, that we should think not only about stability but also security. That can be actually more important in the sense that that can be what players will play. What will be actually more stable, perhaps, than Nash equilibrium. So, formally, similar to what we did for constant sum games, we also can define something which is maximin here. In any game, we can define the best strategy in the case the other player tries to hurt us as much as possible. She doesn't necessarily have a reason, but what if? That's the best pessimistic strategy, the best thing we can guarantee, and that's sometimes called the lower value. That's the maximum over minimum, so the maximum I can do against the worst possible choice of the other person, of the other people, because this is not necessarily a two-player game also. So in the infinite case, of course, the maximum and the minimum may not exist, don't have to exist in general. Now, the good news is that, yes, let me tell also that if they don't exist, I can always talk about supremum and infimum, but then I won't have a value which not which realizes them. So the good news are that for mixed extensions, the fact that the utility is continuous in the probabilities, the minimum of the utility is continuous, and then the maximum, of course, the utility is continuous. Since the domain S minus I is compact, the continuous function minimum gets extremes, both maximum and minimum. So it gets, excuse me, again, the utility being a linear combination of the basic utilities is continuous. So given a continuous utility and using the compactness of S minus I, the minimum is attained. Now, not only is that attained, it's also a continuous function. And then, given the compactness of Si, the maximum is attained. So basically, what we have proven is that for mixed extension, the compactness and the continuity guarantee the existence. And actually that holds for any compact Si and continuous U, I. The minimum exists, and then it also is a continuous function, and that the maximum exists. So let us look at the first example, but I remind you that we assume that we knew that the only equilibrium is bottom right. But what are the worst possible things that the column player can get from the row player? Well, here it's 1, 0, 2. So it's 0. Here it's minus 20, 1 and 3, minus 20. What are the worst possible things, values, utility values, that the row player can get from the column player? So for top it's 1 and minus 2 and 2, 2. For middle it's 3 and minus 10, minus 10, and for bottom it's minus 100 and 3 minus 100. So in the attempt to minimize the damage, or formally to maximize the minimum, the column player should choose the maximum of that minimum. It will be 0 because it's maximum of 0 minus 20. So it will be 0 for the column player. We write it here in this frame, and the row player will maximize over 2 minus 10 and minus 100. It will be 2, so she should choose top. So we already said, right, at top and left, that this is the only pair of max means here. And now let us go further and let us look at another interesting example. So that example is from that book too. Many in that area of security and stability, I use many examples and some statements from that book by Mahler, Solan, and Zamir. So what I want to exemplify here is that there may be several max-min strategies with various utilities which result depending on which max-min strategy is used. So the column player here, the minimum that she can get if she chooses stop, then the worst is between 3 and 0. 0 if she chooses bottom, the worst is between 2 and 1 is 1. So the best she can choose is to maximize over those minima, and that's to choose bottom, and that the maximum will be 1. We write it here in the frame, in the corner. That was what the row player did. Now for the column player, the worst that she can get from the other player, from the row player, when she herself plays left, is the median between 1 and 3, 1. Now when she plays right, it's the median between 4 and 1, which is 1. And here, both strategies are optimum in that sense. They're both max means. Both give 1. So the row player should choose B in order to maximize the worst. However, in order to maximize the minimum. However, the column player can choose anything, and the utilities, the pair of utilities is either that one, 2.3, or 1.1, depending on what the column player chooses. Now, a theorem which is related to that, which we already said, but I think it's nice to again, maybe from a little bit different perspective, having learned new things, have to again go over some existing theorems and to kind of try to deepen the knowledge and to root it in a better way so that it cannot be uprooted by the flow of time. So